Okay, today we're going to be talking about the minerals that make up Earth materials and the layers of the Earth that we've been talking about. Our learning goals for today are to relate the chemical composition of the layers of the Earth to minerals that are found there, to divine and understand what makes a mineral, to discuss crystal structures and the bonds within crystals, and to categorize minerals into classes. Okay, so every year, 38,052 pounds of new minerals must be provided for every person in the United States to make things we use every day. This is an estimate. This is not actually every year, but it's approximately this much. This is an excessive amount of new minerals for each person in the US. So we can break this down into where these are all coming from and going. So, for example, 8,500 pounds of stone are used to make roads, buildings, bridges, landscaping, etc. for each person. 357 pounds of iron ore are used for steel in buildings and cars and trucks and planes. You can even think about how much coal is being used, other metals, things you don't think about like aluminum, how much is going into buildings, cans that we drink out of, cars, airplanes, phosphate rocks. These are used for growing food because we use phosphate in fertilizers. So there are a lot of elements and minerals and earth materials going into the things that we use and consume every day. So just to take an example, something that we all use every day is our cell phone. So take a moment to think about what minerals are specifically used in your cell phone. Okay, so we can break down what minerals are making up different components of our cell phone. So these are called critical minerals. So critical minerals are just earth material minerals that are mined for new technologies. So for example, in the display, we can start with the screen. There's obviously silica, so silicon dioxide or quartz sand. It's combined with ceramic materials and potassium. There's layers of indium tin oxide that are used to make the circuits. Gallium is used for the LED backlighting. And then sphalerite is the source of indium used in that conductive coating that makes it a touch screen. You can go through the same thing. I'll let you go through this in your own time, but all of the minerals that go into the electronics, the circuitry, the battery, the speakers, the vibration capabilities, these all were earth materials that have been mined specifically for this purpose. Just a note, critical minerals and mining, these are growing industries, so this is a reason to pursue a degree in geology as critical minerals become more and more important in our economy. Okay, so very briefly, I'm going to walk through the elemental composition of each of the layers of the Earth because these elements are what rearrange themselves into regular patterns or crystals to make minerals. So starting with the core is primarily iron, as we talked about in the last unit. The mantle, it also has a lot of iron, but magnesium is in greater abundance than iron, or oxygen is in greatest abundance, and then magnesium and silicon are about equal proportions. So you can see we're starting to get more of the silicon and oxygen, which I've told you about before is what makes up the silicon tetrahedron of silicates. The crust then has more aluminum, so you still have that high oxygen and silicon, and then you have aluminum added to this. So all of these elemental abundances express themselves in the minerals that are found in materials from these layers of the Earth. So what defines a mineral? So there's an actual definition. So it's naturally occurring. It's a solid. It forms geologically. It has a definite chemical composition, an ordered atomic arrangement, and most of the time is inorganic. Okay, so going through each of these, we know minerals are crystalline. So what you see at the top here is a disordered arrangement of atoms. So this would be a non-crystalline substance. And down here, you have an ordered arrangement of atoms, and so it's forming a crystal structure. Glasses are not minerals because their atoms are not arranged in an ordered way. So some examples are extrusive volcanic glasses and ashes and pumice. These quench so quickly that they don't form repeatable, predictable crystal structures. A mineral is also a homogeneous solid. So the rocks that make up a cliff would be made of minerals, but the water that is in this pool beneath this waterfall is not a homogeneous solid, and thus it's not a mineral. A mineral also has a definite chemical composition. This means if I say quartz, we know it's SiO2. If I say olivine, we know the chemical formula is iron magnesium 2 SiO2. Potassium feldspar, it's KAlSi3O8. And we know a mineral is inorganic for the most part. So, for example, amber on the left comes from a tree, so you know it's a solid and it's natural, it's organic, and thus not a mineral. On the right, we have galena. This is metallic, so it's inorganic and a mineral. A mineral must be naturally occurring. So on the left, we have cubic zirconia. So these are unnatural, and so these are not minerals. Over here, we have the Hope Diamond. It is a mineral. So I'm going to give you a little bit to think about, and I feel free to pause your video and think about this, but I want you to perform this thought exercise of whether a snowflake is a mineral. So go through the 6 characteristics of a mineral and ask yourself whether a snowflake is a mineral. So feel free to pause here if you want to do this. Okay, so now we're going to think about how atoms bond to each other in a mineral. So there are 2 types of primary bonds with the minerals. There are ionic bonds and covalent bonds. So here you see an ionic bond between a sodium and a chloride, making a salt. And here you have H2O, so water, sharing covalent bonds. So here you see the periodic table, and there are different elements that are more likely to bond together. So for example, noble gases here in the furthest right column, these are unlikely to bond to form a compound. These are inert gases. They're happy just being on their own. These 2 columns to the left of the noble gases have a tendency to gain electrons to make a full outer shell, where their counterparts are over here, the 2 leftmost columns, they have a tendency to lose their outermost electrons to uncover the full outer shell. So elements from these 2 columns are likely to pair with elements from these 2 columns. In an ionic bond, there's a transfer of electrons, so electrons are swapped. So as I was saying, some are more likely to lose, and some are more likely to accept new electrons. Here, the metal, atom 1, is transferring an electron over to the non-metal in atom 2 in order to form an ionic molecule. So going back to that example of sodium chloride or table salt, there's sodium, the metal, is sending an electron over to the outermost shell of the chlorine to form an ionic bond. And here you can see the crystal structure of sodium chloride. it makes the mineral halite, which is just table salt. And you can see the sharing of the electrons is forming bonds between sodium and chloride. Now, covalent bonds are when electrons are shared. So here you can see in these two ions, they're sharing their two outermost electrons. An example of a covalent bond would be an elemental sulfur. So between all of these sulfur ions, you have shared electrons. So it's critical to know how atoms are arranged because they can have the same chemical composition but be different minerals. For example, both graphite on the left and a diamond on the right are made up of pure carbon, but they're very different minerals. So diamond, it's typically translucent, it's extremely hard, whereas graphite we can pretty easily break. So when you have the same elemental composition but different minerals, these are called polymorphs. So same formula, different structures. So graphites form these platy structures that flake apart. So the carbon atoms have strong bonds along these planes, and then weaker bonds that are holding planes together, and that's the breaking surface. Whereas diamonds have this interlocking, strong structure. So here we have galena, which is a lead sulfide, so one lead and one sulfur. It has a cubic structure, and you can see the bonding between the lead and the sulfur. Another example is muscovite. So this is a potassium-rich phyllosilicate. So it's another platy mineral. So there are these tetrahedra that have of the silicates that have strong bonds. Then there are weaker bonds in between each of these tetrahedra. That's what makes this platy mineral that you can actually flake apart the layers and break these weaker bonds. Okay. So focusing on the crust is made up of primarily silicon and oxygen, and so it's made of silicate minerals. So the silica tetrahedra, SiO4, is the basic building block of most crustal minerals. So here you have one silica, 4 oxygens. So silica polymerization is how silica tetrahedra are organized in different ways to form different minerals. For example, going back to that mica or the muscovite I was showing you, silica tetrahedron likes to form these stable plates, and then there'll be weaker bonds between these plates forming little sandwiches. Amphibole just has fewer of those ring structures, and pyroxenes have these sort of like chain silicate tetrahedra. A few common silicate minerals that you'll see in your mineral lab, so there's feldspar, muscovite, quartz, olivine, pyroxene. This is just to show you how different rearranging silicate tetrahedra and adding in some other elements can make your minerals look. So how do we classify minerals? So they're classified typically by their dominant anion. So I've talked a lot now about silicates. So these are rock-forming minerals. Oxides, these form, think like rust, iron oxide. These form, magnetite, hematite. You can have manganese oxides, etc. Sulfides, they just have a sulfur. Pyrite and galena are examples. Sulfate minerals, so a calcium sulfate would be gypsum. Halides, these are like sodium chloride, or fluorite, which has a fluorine. Carbonates have a carbonate ion, so you burn calcium dolomite. And then there are native elements, so these don't actually have to bond with any other ions to form their mineral. So you can have a copper mineral, you can have graphite. Again, diamond would be a native element. Here are just some pictures of what these look like. So here are, there's a feldspar. You can have different, you see different silicates, uh, pyrite, which is fool's gold, halite, which is table salt, seashells, these are made of carbonate. So next class period, we're going to talk about chemical sediments, and those chemical sediments are primarily made of these sulfates, halides, and carbonate minerals. Okay, so final thing, what is a rock? So today we're just giving crash course in minerals, but a rock is just an assemblage of mineral. It's usually an assemblage, but it can be monomineralic. So what I'm showing you over here is a granite. So these form in intrusive igneous environments. You probably have seen a lot of them in countertops. But the granite itself is made up of an assemblage of minerals. So you can see these more translucent, whiter minerals. These are quartz. The black minerals that look like spots or freckles, those are hornblende. The pinker minerals, these are potassium feldspar. Okay, and that's it for now for minerals. You'll get a lot more information about minerals in your minerals lab. But next time we're going to be talking about chemical sediments.